Welcome to the Mission Matters podcast, a podcast from Shield Capital where we explore the technical opportunities and challenges of developing and deploying commercial technology to national security customers. I'm Maggie Gray.
And I'm Akhil Iyer.
And we are your hosts from the investment team at Shield Capital. All views expressed by the hosts and guests on this podcast are solely their own and do not reflect the opinions of their employers or investment advice. References to any securities are for informational purposes only and do not constitute an investment recommendation or offer to provide investment advisory services. In this episode, we're joined by Schiller and Aeden Gasser-Brennan, the founders of Rangeview, a startup revolutionizing investment casting through novel 3D printing techniques that are enabling the next generation of autonomous systems and advanced manufacturing. Investment casting is an ancient process. It's been around for thousands of years, used to create everything from jewelry to jet engine components. But despite its importance in manufacturing critical parts for aerospace, defense, and automotive industries, the fundamental process has not changed much since the 1960s. Meanwhile, the U.S. has lost over 100 investment casting foundries since 2001, creating a strategic vulnerability at a time when our defense systems are becoming more complex and our adversaries are modernizing their manufacturing infrastructure.
And what's particularly striking is how this old school manufacturing process has become a bottleneck for innovation. As companies like SpaceX, Tesla, Anduril, Varda, as well as more established aerospace and defense companies are pushing the boundary of what is possible with manufacturing modern systems, they're discovering that traditional manufacturing just can't keep up. They need components with complex internal geometries that are really impossible to create using conventional casting methods. Think turbine blades with intricate cooling channels or missile components that need to be both lighter and stronger than ever before.
Enter Cameron and Aeden, two college students who saw an opportunity to bring this ancient industry into the digital age. By combining custom 3D printing with advanced material science, not only are they making the casting process faster and cheaper, they're actually enabling an entirely new set of designs that were physically impossible to manufacture before. It's not just about efficiency. It's about unlocking new capabilities for America's most innovative defense companies. Cameron and Aeden, thank you guys so much for joining us.
Thank you for having us.
Awesome, guys. Cameron, Aeden, so excited to be here with you. It's been awesome. Since the time in your Berkeley lab a couple of years ago to where you are here now in El Segundo, it's been awesome to see the journey, what you've built, how you've executed. Before we dive into all of that and honestly maybe share with a good amount of the listeners what investment casting actually is, let's actually start geopolitically. So last couple of weeks, a lot happening in terms of geopolitically as we think about both tariffs, as we think about the state of the nation's industrial resilience. Would love maybe just to start out with where do you think we are in terms of the state of U.S. manufacturing? And we can sort of dive in beyond the generalities because you're living it on a day-to-day basis. Where are we at? What's your assessment of that? And where does sort of your work fit in?
Yeah. Well, I mean, the state that we're in is, everyone that's listening, kind of take a look around right now and see if you can find anything that you can confidently point to that was made America. It's not great. Slowly over the past 20 years, we have let it all slip overseas. And globalization and the whole story about how we got to the place that we're in right now. But the truth is we've really hollowed out our industrial base for the promise of more freedom and flexibility. And what we got on the other end was a supply chain that's more fragile than ever. The great Americans that are responsible for making all of the stuff that is underpinning our critical defense systems and also everything else in life. Those great Americans are retiring. In fact, most of them are on their way out or out already. And there's less and less folks to make the parts that we need. And they're all overseas now. So for defense applications and for energy applications, a lot of these critical components, we're tripling the energy usage needs with the AI boom coming. And there's just no supply chain on the back end of it. So I'm excited to talk about that in more depth today. I think most folks don't know just how bad it's gotten. And that could be a real big awakening for us if we ever need to pull that lever and start to make lots of parts the way that we used to.
Definitely. And Cameron, it's not just necessarily the globalization piece, but having watched you over the last couple of years, it's the ability to innovate in the fast feedback cycle between what is really some new novel systems, platforms, both civilian and military. It's kind of hard to do that when you're shipping a part every week or two from somewhere else, when the cycle time to be able to accelerate that is not just in the production, but actually the unique design aspect.
Yeah, that's exactly right. That's a big point that I think lots of people are starting to pick up on now, is when you're building a system, the first thing that good engineers do is they engineer iteration rates. And the easiest way to collapse iteration rates and get to higher levels of innovation, or to bring manufacturing as close as possible to the final design scape. So some of the most innovative folks out there are actually doing their own manufacturing. They understand the constraints of the system that they're building. There's this great art that's been lost in America now, which is called DFM, or design for manufacturability, and that is at a cultural level what it means to know how something actually gets put together. We lost that a little bit, and believe it or not, most of the innovations that happen in the design space of design for manufacturability. You can't just make something that's new. You have to make something that's new and that can move its way into the world. And so understanding manufacturing is critical to innovation. And the way that you understand manufacturing is you do it. So we need to do it so we can collapse those design iteration rates and really bring the best and brightest designs to the to the end user, the warfighter.
I think there's a point to be made. I mean, early on, when we were starting the company, one of the things that I think was a clear indication that the paradigm of, we're going to do all the design here in the US, we're going to ship the manufacturing drawings overseas, and we're going to get stuff from low-cost countries, and we're going to make all the money because we control the designs, we control the brand, but we don't do any of the hard work. The signs that was collapsing, I think, were the Chinese consumer electronic companies starting to kill the American. And the greatest example of this is DJI, right? Like DJI, which is now obviously extremely relevant militarily, but back then it was just a consumer electronics company. And like, why does DJI do so well? It's like a good question, right? Why are they so much better than all the American drone companies, at least for a while? And I think the answer is they could manufacture everything down the street, right? So their iteration rates were incredibly fast. They could do more technically interesting things at lower cost and get those to market faster. I mean, it's like a pure advantage if you're a manufacturing company or a company that makes a product, is to be able to iterate quickly. And so that was like this really clear indication that something is wrong, right? Because the theory is, Americans, all these big universities, we have the best engineers in the world, we're going to make the best products. This doesn't work if you can't manufacture those products in-house, and you can't do that, iteration and development quickly.
And why is it that we lost so much of that capacity? And, what are the levers that we are actually able to pull to bring that back to the US?
So I have this kind of saying, it's like the right industrial policy is the one that actually changes the unit economics of manufacturing in your country. Like everything else is a short-term solution. But as long as it is actually really more expensive to manufacture here, new manufacturing will come back. And so actually, I'm a bit of an outspoken believer in tariffs, because tariffs do this, right? This is like strictly, it is more expensive to manufacture here. But I think China's a great example, right? It really is worth looking at, what worked so well. And obviously it started with labor, right? This is why we started sending things overseas. But over time, like China's real advantage today is that they are consolidated and have a ton of things in close geological proximity. And they have this ability to go and get things quickly, build new things quickly, and like deploy new technology out to the factories quickly. And so I think
like they can literally walk down the street and talk to their friend who's actually doing the castings or forgings here.
And then redesign a part in the course of a couple days or hours.
And then not only that, they can go down and they can buy their ceramics feedstock from their friend 3 streets over, and the mine that's making the raw, iron is only, a few miles away, right? And so it's like this real, consolidation of all these different processes in close proximity is the real benefit. And I think this is a huge project to build this back in America. We had this, right? America was the king in manufacturing up until, around the 80s or 90s. And so I think you have to start in the places that have some sort of DoD significance. And so the interest is there from the government, right? You need to start with who actually wants the manufacturing back the most and start building it back capacity there. And I think there's a flywheel to get started, which is if you start in the processes that are the most critical for the people that care, those processes will make it cheaper to do all the other processes here, right? This idea of learning curve, but there's also compounding learning curves in all of manufacturing, right? The more of everything you do, the cheaper it gets. The more of things that are adjacent to the thing you're doing, the cheaper it gets, because you share labor and you share equipment and things are amortized over more parts, right? Like there's all of these effects. I think policies that the government has pursued have been a little misguided in a few key ways. And so one is the government's really good at funding development. And I think they love funding development. And there's a bit of an issue in that a lot of things get developed on government money and then never go to production. And there's not as many incentives to actually build a lot of capacity. And so I think if I were to change any of the industrial policy that we're doing, it would be less on development contracts, less on qualification contracts, and more on, if you build this amount of installed base capacity, we will fund your capex, or this is a tax write-off, or something to this effect, because this actually changes the unit economics. A million separate funding development of something, a million early stage contracts proving out new technology, it's pretty misguided. It happens, right? Is like America develops all this amazing new technology, and then China implements it at scale. It's a story you just see again and again and again, right? America invented the CNC machine, and yet, I don't know what percentage of CNC machines are in the US. And this will happen again and again, so long as the government is just funding development. And I think China's a great example to look at, right? Funding CapEx, cheap financing from the government really does actually drive lots of growth in manufacturing. And it's because it's geopolitically relevant for them. It's geopolitically relevant for us too. And so I think we'll start to see this happen more and more. But I think there's been this kind of history of funding development where really the thing to fund is scaling more similar processes that have less of a technical moat to get across, less difficult thing to develop, and more about just scaling lots of capacity.
So Aeden, here we are talking about manufacturing. You're focused on investment casting. There's probably folks listening in, or even frankly, when I was first meeting you, I had to learn a ton about what investment casting was and what you're doing with it. That's so novel.
Yeah, so I'm going to walk through each step of the process and explain what we do, what a traditional foundry does. And I'll kind of explain it from the customer's view, right? Because that's who matters at the end of the day. And so, you're a customer, you want to make a part. You come with drawn in CAD file, bunch of requirements. And so these requirements, what are the mechanical properties of the part? What kind of processing is allowed? What shape is it? How do we measure the shape? All these things, right? And you start out Foundry. We do the same things. We look at this. We say, okay, how are we going to make this part? How are we going to set it up? What's the right process to make this? And for us, it's largely similar across a lot of parts. For Foundry, it's actually very different. So, they're making some tool to start, right, which is a big block of metal. And that block of metal has the shape of the part cut into it. And usually, it's actually tweaked in a little way because the part might deform, might change shape during the process. And so that Foundry is going to start by making a wax pattern. So Rangeview doesn't do this. So the Foundry has a wax pattern, and then they're going to go and assemble a bunch of these patterns together. And so if you want to make a spoon, you have a wax spoon. And you'll see how that works in a second. And so you might take a bunch of spoons and put them together. You'll have a wax tree actually feeding them. And so you have this big wax tree that makes a bunch of wax spoons. And then what you do next is you dip that in a ceramic coating. And so usually you dip dry. It takes a few weeks. And actually what you're doing there is building up a layer. It's like a clay layer on the surface. And then what you do is you melt all the wax out. Then you actually have to burn the wax again. And then finally you fire the ceramics. You've got basically a big complex mug, if you think about it that way. Right? It's a big ceramic mug. And so what Rangeview does is we just make the mold directly. We print direct molds. And so we skip all of these steps. We skip all the manual labor. And really importantly, we skip all of the technical characteristics of the final part being driven by a human's decisions, right? You want the technical characteristics of the part to be driven by software and by a machine, because then it'll do the same thing every time. Your tolerances are much tighter. You can rely on this process much better. So at the end of that whole process, you've got a part, which is a big ceramic cavity, right? And then you pour metal into it. And so variety of different casting processes. Rangeview works with a very particular one that produces very reactive alloys or very high temperature alloys. And then you pour the metal into this mold, and then you remove the ceramic after it's cooled. And so you end up with just one part, right? You have to throw away the ceramic. You remake the ceramic every time you make a new mold. And this is how you make the part. And then you cut the part off the tree, and then a ton of post-processing. Right? So you might take x-rays of the part to look for porosity. You might coat it with a penetrant that shows where cracks are. You might take some of the parts and cut them apart and pull mechanical tensile bars to know how strong they are. Then you'll heat treat them, machine them, coat them, and then generally at that point you'll have a final part. And so the whole process, right? You have all this fixed tooling that's involved in making the part traditionally. And for us, it's just the same process every single time. We're direct printing a ceramic mold. This is a a process we've built in-house, and it allows us to do this whole process for different parts without changing any tooling. And so today, the US is in this place where we've offshored almost all of our investment casting capability. And investment casting is used in enough of these kind of commodity capabilities that it was like, well, this isn't defense critical. Maybe we can push this overseas. There's actually a lot of cases where actually people got ITAR exemptions to go overseas and manufacture ITAR critical parts overseas because it was a little cheaper. Investment casting is full of labor. The traditional process has hours and hours. You might have 40 hours of labor going to a little part that fits in your hand. And so case, it really matters if you get another $20, $30 out of your labor if you have a very unautomated process, which is kind of the traditional method.
That's awesome. And it sounds like the previous instance, that hasn't changed for thousands of years, right? Some sort of wax base to a ceramic, you pour metal into it and grate.
Yeah. This is a beeswax, right? We started with. It was beeswax and river sand is how this process works.
But critically also now being able to, because you're 3D printing and designing and in this digital foundry way, actually be able to make whole new set of complex geometries that then you can core wherever you want.
Correct. Yeah. And we're enabling a whole bunch of designs there that, you couldn't make in the traditional process. And those are, some of the most exciting parts we make. And then it's also worth saying that almost every one of those post-processing steps I described generally are done by people. So the way you cut the casting off in a traditional foundry is a guy sitting on a saw. This is a horrible job, right? This is a super dangerous job. It's super loud. The saws break and send pits flying. People die doing this, right? It's really a horrible place to work. It's not somewhere that I'd want to work. It's not somewhere I'd want my kids to work. And the same thing with everything else. The person grinding the part, the person heat treating the part is a bunch of people stacking parts in a big furnace, closing the furnace, opening the furnace. And so in our factory, almost all of this is done by a machine, right? A person is programming the machine. They're setting it up to do a new part, but they're not the one actually cutting the part. They're not the actual one grinding the part. That's all done by a robot, really, at the end of the day. And so the traditional process to make any of these parts and any of the traditional competitors have a very, very inflexible process that cannot be changed without huge, budgets. You're making a part, you want to make it slightly differently. You want to iterate it on a design. You could be $2,000 in the hole. It could take 6 months, a year, 2 years. This is very, and the second piece is there's huge amount of extremely skilled labor that goes into this. That's really hard to scale. And so if you're an investment casting foundry and you want to get bigger, you want to double your capacity, there are no people you can hire, right? These people have all retired. And so the things that are build factories that are not dependent on specialized human labor to make components and are not dependent on tooling to make parts. And so what these foundries look like, right, is you want everything to be made by a computer. Right? How can you give the computer the tools to make your casting? And so we use a kind of variety of different processes that make sure that each manufacturing process in our factory is software defined. And so this starts with making molds. You want to make sure that the molds can be made in a software controlled way. So we've done a huge amount of innovation on the process there and the equipment and the materials to make sure that when we make a mold, there is no fixed tooling that's associated with that, and you're forming it all digitally. And the same thing with every single piece of equipment and process that comes after that. And you have about 8 or 9 steps in our process internally to do that. And each one of those, we have a digital definition, and then the machine is running with telemetry, going back to the system and running to the prescriptive definition that we've given it for that process. So this is pouring. What temperatures do you pour the metal at? How fast do you pour the metal? What kind of environment around the metal? The vacuum levels and things like that. And so the big thing is our factory is not running on very highly specialized labor. It's running on software controlled equipment that can form different parts with just changes in software and without retraining people. So then maybe that gives a high level. I can dive into all kinds of details, and I'm sure Cam can talk to that one too.
Super helpful. Maybe one more high level. Just walk through, if you can, even just a couple of the steps from design to 3D printing to cast. What does that sort of look like?
So the traditional process here. And what an average aerospace customer says, they want to make a turbine blade. They have some preliminary design, and then they want to get into production. First they have to get to design validation, but the goal is they want to be making turbine engines in 6 years at rate. And so generally what will happen is they'll go out and they'll go to as many foundries as they can, and they'll try to find someone who will bid the part. And this is the first thing that's surprising. Is like most of the parts get no bid most of the time because most foundries are overbooked and don't have capacity and also can't scale, right? They're stuck because of their labor. So the first process for the designer, right, is that you as a customer is to try to find someone who will bid on your part. And you might not have a finished design at this point. And so you're going to tell them, hey, look, I want to make a few of these. I want to do some prototyping. And generally, they're going to give you back 2 really important quotes, right? One is, here's our upfront quote and here's our piece price. And the upfront engineering and tooling making, maybe 300 grand for a part, might last, 6-8 months. And then you'll go into that. And then you'll also get a huge amount of technical documentation. So for each of these parts, if you're making a turbine engine, you might have 100, 200 pages of technical documentation for a little part. And what that is that's a contract between the design engineer and their requirements and the foundry. And what the foundry is agreeing to is I'm going to meet all of these requirements. And it might take many iterations to meet these requirements. And so for the foundry, every single one of those iterations is iterating on tooling, retraining people to work on the new parts, and trying to hit those requirements. And then that's what stretches it out. For us, when we receive something, so we'll ingest it, we'll do some design, and we can essentially just put it straight onto our printers, which make the molds for the casting, and then get results quite quickly.
And these are 3D printers, right? Standard 3D printers.
So yes, so we use a bunch of in-house developed materials and process to make these castings and molds. Essentially, we're forming the geometry that's going to form the part with a printer. The end part is actually just a normal casting, and so unlike a lot of the additive processes, the metal 3D printing processes, there's no requalification, there's no retesting. The material properties are the same as these casting alloys have been developed, for 50 years. And then we get a part straight out of that process. Maybe that gives a high level. I can dive into more details.
Thanks. Cameron, if I can come back to you on the discussion we were having around the iteration cycle, can you walk through an example with whether it's a real or hypothetical customer, what you have done here, both Digital Foundry and the novel casting process, the full life cycle has just allowed for that incredible acceleration in both speed and scale.
Yeah, absolutely. And I'm not able to use direct customer names in the line of work that we do, but I'll give an example of something that we see happen and how ultimately it results in American supremacy on the battlefield. So as Aeden was speaking about a little bit earlier, when you're making a part, the end designer is actually just delivering a capability. And that capability may be, let's build the engine that can fly the furthest, or let's build an engine that can fly the fastest. And ultimately that comes into a balance with reality and physics. When you try to put those metal particles through their paces in a jet engine, it's going to be how hot you can get it. A really common one that we see, because we do a lot of, turbine blade work, is what's the exact shape of that turbine blade? And we've gotten good at simulating physics to some level to help us figure out how the air might flow through that turbine blade. But the real way to figure it out is to put it on the test bed and let it run. And the simulations are never perfect. Simulations are only as good as the data you feed them. And so there may be a few variations of how that blade should be shaped that a designer is looking to go through. And what they're really trying to figure out is what shape is going to be the best for production on this engine. And every form of manufacturing has some inflexibility associated with it. The way to think about this is in manufacturing, the term is called tooling. And tooling can be hundreds of thousands to millions of dollars to set up a set of machines to do a set of instructions. And this tooling is hard coded. It's coded in the actual cavities of the molds that you're producing. And so when you ask that tooling to do something a little bit different, to figure out if that little bit different shape on the blade results in a little bit more or a little bit less performance, you have to pay hundreds of thousands or millions to change it. But you're locked once you're in, you're good to go. And so the qualification process of a lot of these components often involve changes. And when you move that tooling from a physical world to a digital world, you unlock a whole other world of possibilities, not just for cost reduction, but for achieving the optimal design. Now, there's this other kind of intricate layer that that's starting to come into play as America becomes more serious about producing. This is maybe a bit more general of a comment on the state of the DoD world right now, but lots of folks are delivering to kind of low rate initial production. But a lot happens when you go into full production. And we're talking about, what is the capability, not just to make engines that fly as far as possible, but how many engines can you really make a year if you had to make every single engine that you could, right? And it's a different scenario when you have to hit full production. And in many cases, when people are designing today for these flexible manufacturing technologies, they're using a different manufacturing technology. You might metal 3D print something because then your tooling is digital. But when it comes to make full production, you're moving to a traditional form of manufacturing. You're moving to casting. You're moving to, stuff that just, it scales. So one thing a designer has to look at is how serious they are about production. And if you're serious about production, you're going to design to the constraints of the manufacturing technology that you use to scale production. And so this is one of the core beliefs that we coded into our technology stack. Our technology is capable of iterating on quick turn qualification to allow that part designer to get the shape and the blade that they want. But at the flip of a switch, they can go to full rate production with the same constraints, the same casting constraints. We don't have to change our blade thicknesses. We don't have to change our overhang angles. It's directly the same manufacturing technology. And then I'll give you another one, which is on the tail end of this. So we've seen this with past sustainment issues before, but at the end of a life cycle, you store that tooling, and you store that tooling on a wall, and you're making the next newest and greatest part. And that tooling, believe it or not, it'll get lost, it'll rust, it'll wear down. The tools wear down over time. And when you go to pull that part back off the shelf, when you need to make 14 joysticks because a plane is down and that joystick has to be remade to put it back on, you have to build up that $100,000 tooling, that $1 million tooling all over again, just so that you can serve a hilariously low quantity that the industry calls alien castings. They literally call them alien castings, or these onesies, twosies that they need just to sustain stuff. So you have this other flexibility request on the tail end of these programs. And once again, this is what we've designed our production technology to do. And I think the bigger picture when you zoom out from all of this is you're looking at manufacturing holistically. You look at the problem. It's not just about making one part. It's about making a process that can consistently make things at scale. And that's what Rangeview is about.
That's right. And that's your sort of idea of the digital or cyber foundry. Cameron, what's a cyber foundry? What's the vision for it?
Yeah, Cyber Foundry is Rangeview's first product. And the Cyber Foundry is simply a factory that is making America's most critical componentry with the workforce that America has and with the technology that we invent here. So it's a collection of custom built processes, materials, and equipment to make a digital file of a part, which we've gotten really good at building in America, to turn that into an actual part, a real part that can be certified and clicked into a plane, a ship, a vessel, and unlock the capability that systems that we've designed so well, and they've been hampered by not being able to be made. We unlock that problem for the US DoD and our other partners.
That's awesome. That's from digital design, iteration, digital manufacturing, and then actually the real hands-on production.
Every stage. I mean, our factory is just as much of a computer as it is a metal shaping device.
Yeah, I think it's worth saying a big part of our philosophy is the next generation of American manufacturers have to have a huge amount of engineering expertise in-house. You're not going to innovate on process if you don't have the expertise on how your process works. And it's really important that the manufacturers, not just the designers, but the actual people that are designing the process, building the equipment, setting up the factory, know what's going on, are incredible engineers.
What role do you see for new technologies in accelerating reshoring of manufacturing capabilities to the United States? And what are those technologies that are actually going to drive those trends?
Yeah, and maybe, Maggie, in addition to that, to your earlier answer, Aeden, we can't necessarily replicate what other nations are entirely doing, right? We have certain comparative advantages here, and you guys, among many other things, are innovating from a technological standpoint, right? From both a digital and actual physical, right? The software-defined aspect. So a little bit of a addition to Maggie's question. One, how much can we actually rely on just technological innovation as part of it? And then what else needs to be done?
Yeah. So technology is the way forward. It is the only way forward for us, but that's a great American trait. America knows how to do that. And it's not that complicated. The first thing you got to do is pull your manufacturing technology into the 21st century. I mean, it would blow you away if you walked into a foundry today. All the folks, the heat treat shops, the anodize shops, all those folks need to pull, their furnaces into the internet. They need to bring laptops into work and just run it the way that a modern company is run. And so I don't think that's reinventing the wheel. I think that's getting more folks into the industry. So, it's tough because the factory owners, that was a bit of our origin story, is we were just two robotics kids looking to sell robots to factories. We, what a journey. We thought that manufacturing was further along and it was just ready for someone to sell robots. But the truth is they didn't even have the outlets on the walls. So we had to go down to the studs and start there. So, I don't think it's reinventing the wheel. And there are many companies doing this right now. I mean, go look at Suncut Send. It's this amazing company that chose their manufacturing technology. That's a good way to think about manufacturing too at a company level. You go to the processes. Manufacturing is down bad as it is in the country. It's actually still a bigger market cap in America than all of tech combined. And so if you think about it, you can't compare a fintech company with a healthcare company. They're completely different sectors doing completely different things. And in manufacturing, the process is the sector. So there's this amazing process, sheet metal fabrication, that, you're making stuff out of, really strong paper, doing origami to really strong paper. There's this company out in Reno that just figured it out. It's founder's a software engineer that came from doing SaaS work. He's just, wanted to help his country out. And he's built this amazing shop that's just, yes, it's software enabled, but it's just the modern tools of manufacturing, put into a process. I think a lot of this is going to come. And I think this is what's happened elsewhere. There's this strategy that China used when Xi Jinping was building. It was an actual initiative you can look up. It's called the Made in China Initiative. And they very cunningly required American firms, in order to access the cheap labor and other subsidies associated, required a partner, Chinese factory partner, to learn what you were doing. And of course, we now learn what happened is we taught them all how to do it, and then they kicked us out. Uber, this happened with Uber. This happened with Google. They were operating in that market. They told them how to do everything, and they're just a one-for-one move over. Chinese factories are probably running the best processes right now in the world. So I've seen a few places there where you kind of flip the script and you say, well, there's some great Chinese manufacturing approaches. All the equipment is modern. You go buy the best manufacturing equipment. I mean, we didn't just lose our factories, right? We lost our equipment makers. There are no factories to sell to out of business. So, if you want to see what a really good piece of modern industrial equipment looks like, natively digital, it's got an Ethernet plug, goes straight to the modem and the router, and which is why you have to be careful. But just go look at the way that those machines are built overseas. So maybe there's an opportunity there. But we really don't have to reinvent the wheel. We just need to get a lot of folks interested in doing this again. I think Aeden's totally right. You set that up by getting the unit economics right. And the unit economics are really, really wrong. Technology won't do it alone, unfortunately. I wish you could say you could innovate it away, but if you do a little bit of Excel, it's frustrating. You look at some of these parts, the part costs more to make in America if you just paid for the electricity and the metal than it does to have a fully turned part in China. Unless if you can develop technology that makes the metal free or the electricity free, There, 99% reduction in labor because you have this perfectly automated factory. Equipment that costs $1 because you figured out how to scale this stuff to the moon. It doesn't matter. You're still losing. That's because of subsidies, and that's because of these vertical integration. It's been weaponized. We've totally come up across weaponized industrialization overseas.
Maggie and I come from the other part of California, the Bay Area, where you can't throw a rock without talking about AI. There's aspects of AI, or let's just call it software defined generally. But as you look at the sort of AI space, a lot of it's digital, but fundamentally a lot of it's moving to the physical world. What actually makes sense, and I hate using AI as a sort of, we sprinkle it in our coffee, but where does it make sense to actually apply either a machine learning or some other artificial intelligence capability when it comes to the physical domain?
So the truth is, it's much harder to build stuff in the physical domain. It's much harder to build stuff in the physical domain when you have, extremely safety critical applications depending on it, right? And so it'll be a while before an AI system can make a decision that is accepted by, one of the, as we talked about, conservative aerospace primes. That said, there's so many parts of operating a factory that are not as critical where it comes in first, and places where things are going to get verified by a human eventually, verified by a test. And so, we do all kinds of things at every level of this, right? From, extremely simple things, right? Like how we inspect parts. There's a whole bunch of things that are normally done by a human verifying that a certain number is less than a certain number and greater than a different number, right? And we do a lot of that with software, and a lot of that with, I don't want to call it AI, but more sophisticated software systems, often that are trained on a lot of data, and it's those same kinds of approaches. At the very high level, we've started to toy around with, an LLM that has access to a huge amount of the data in the factory. Is it making all the critical decisions today? No. Will the software get there and the technology get there that it can sometime in the future? I actually think probably yes.
So AI is only as good as the data that it's fed. And the amount of data that we have, for instance, in something like self-driving cars, it's like orders of magnitude above the amount of data that we have on part making. The first problem is part making data is in the heads of humans that are retiring right now. This is the first problem, right? Let's get these into the computers, right? And then after that, we can start to put sensors in place and directly train that system. So I think a good goal is for computers to know just as much about part making in a few years as they do about driving cars.
Cameron, you talked about addressing this via technology, processes, and people. I want to actually come to the people part, and we can dive into more the other two. People, I'd love to get your take on sort of talent, what you just talked about. But actually, first, I want to come back to your story of you both in Berkeley working on robotics. I remember first meeting you all on somewhere on Shattuck at UC Berkeley in a small little place. Share a little bit about where you came. You shared that initial story about wanting to sell robotics, and then you turned into casting. What was that story like?
Yeah, and you met us at Berkeley. We were a garage, one of the garage startups. So in a garage before Berkeley, it was a huge upgrade to this old Sprint store in downtown Berkeley. Boarded up windows because Berkeley is a crazy place to build what we're building. But yeah, you're right. We met you there. It was a great day. Yeah. I mean, we wanted to reindustrialize America, and we thought that the way to do it was by building robots. And I think a lot of folks see this right now, where we just have to add modern technology. We have to automate. We have to bring robots in and have the robots do the human tasks. We tried to do that. Rangeview was actually Rangeview Robotics. That was our formal name that we pivoted.
And that came from because you both were robotics champions in high school, right?
Oh,
and
yeah,
I think competitors too at one point. Is that right?
Yep. Yeah, we were competitors. Aiden and I have known each other for a very long time. We did competitive robotics against each other. Los Angeles BattleBots. The fighting ones on TV. But even before that, Aiden and I did a lot of high school robotics. And by the way, amazing program. Talk about getting. I don't know if I'd be doing this stuff. I mean, if you'd be doing this stuff if robotics wasn't a big part of the early education system. And it was amazing. There were some fantastic people who built that whole system out. First, Vector Robotics. There's a lot of great stuff. China's doing a really good job at robotics education too. DJI actually built probably the best robotics student competition in the world. It's called RoboMasters, and it's incredible. There are roboticists in China who are, held to the cultural significance of like a quarterback in America, which is that's crazy to me.
Yeah. You got Texas football, and then you have a DGI roboticist.
Yeah. It's just a little bit different in America. It's hard because I think Aiden and I were definitely on the nerdier side growing up. So, I wouldn't say that, people put it this way. People weren't inviting us to parties because we were good at robotics. Maybe one day that'll change. It depends on how much we really need robots to build. I think we really need them to be built. So, yeah, competitive robotics. That was it. But we looked at it and we said, wow, we need to decouple from labor. There's no way America, with our way of life, will ever be able to support the hourly rates of overseas labor. And if we're going to automate manufacturing, this is a big question. Everyone wonders, like, why manufacture in America? Why don't we nearshore to another country? But the truth is, if you decouple labor from the manufacturing cost function, it doesn't matter where you make it from a cost perspective, and where you make it will bring all the jobs. The people that build the factories, the people that build the robots, the people that manage
it still means that people are critically important, but their value is being accrued in different or complementary portions.
Think of it this way. Think about a farmer. A farmer is an amazing roboticist. They're doing the work of thousands of people with one big tractor. The tractor maker didn't replace those jobs. The farming industry and agriculture, there's abundance everywhere, and we can go out and specialize and do all of these great things. But what you're doing is you're giving a human leverage. The comment that I made on manufacturing in America is it's critically important that leverage becomes American leverage. So we have to build factories here. Not factories for everything. We don't have to make plastic forks. There's some stuff that we should share across the globe. But for what we're working on, we chose very specifically to work on the things that America deserves to be excellent at.
So you went from Rangeview robotics to just Rangeview.
Yeah, we just lost the robotics. It's like just Rangeview. It's clean.
But you haven't necessarily lost that mission, because a lot of the components you're now providing will absolutely carry forward in terms of whether it's robotics or just the autonomous system wave of the future.
Robotics is in our DNA. Yeah, at Rangeview, robotics is in our DNA.
So we're saying that the counterfactual between two people losing their jobs to robotics is not actually, it's not automation or no automation, jobs or no jobs. It's actually, we don't do manufacturing in the US and no one gets any jobs, or we do it here and it supports people at the labor rates that they want to be paid here. And it's either good jobs or no jobs. That's the only counterfactual that there really is. And so it's a huge part for the factory to have very few low wage, low skilled positions, right? This is not what Americans want to do. It's not what the next factories are going to be like. And it's not actually how you make good parts at scale, right? You don't want to be reliant on people that aren't that motivated to be there to make your parts.
So, at least my sense from the outside is that the manufacturing industry, aerospace and defense industry is a pretty conservative industry. What does it actually take for you guys to build trust with these customers and for them to entrust you with building some of their most critical components?
Yeah, I think Aeden's got a really good bit on this, so I'll give it to him. But these systems already exist, actually. There's an entire quality industry whose whole job is to take the liability of ensuring that a part does what you say it will do. And that is something from day one we have designed for. Because there have been other innovations that have been hung up on this that said, well, if we just make a cool enough thing, people will want it. And the truth is, you have to be able to prove that part will behave the way that you say it will in order for it to have real value over time. So I'll kick it off to Aeden here for comments on qualification and what that all means.
Yeah, no, it's actually a good question, because I think there's a lot of noise that comes from a lot of new manufacturing technologies about how hard it is to qualify. I'm actually a little bit less sympathetic than you'd think to this. I mostly think this is the case of that technology not actually performing. if you actually had the data to show that your process produces parts that are good enough, you actually probably don't have a huge issue qualifying. The issue is when you fail a spec and you need someone to change their design or redesign their system. And that's where big problems show up. And so for us, a big thing is, we're not doing metal 3D printing. We're not doing some new process that requires totally new design allowables and new designers to be trained up, because the truth is those adoption curves are extremely long. I mean, that's what's happened in metal 3D printing, right? You've just seen these companies that have amazing technology. I mean, I love laser powder bed fusion, but it's not a technology that's going to scale immediately to cover the whole industry. And it certainly isn't going to scale to cover the parts that were designed in the 70s. And the designer's not only unwilling, they're actually not even working anymore. They're retired. You're not going to change those parts. And so the way that aerospace works, right, is there's these long campaigns to make sure that your part meets specifications, right? There's this contract between you and the designer, and you just go through the test. And if you pass the test, it's objective. And so for us, huge thing is just always talking to designers, understanding what they need before we're even making parts, and making sure that we're building a factory that goes in that direction. But the truth is, if you make a technology that has advantages, if you have cost advantages, and in fact, you can meet all the technical requirements, there aren't actually so many issues. The issue is when you're trying to do something new that pushes the designer in the wrong direction.
That's right. And Aeden, it's not just the cost and technical requirements. You are fundamentally, with the way in which you're orchestrated your digital Rangeview foundries, you can make novel parts.
So that's the biggest thing is when someone designs a part, goes through a long simulation testing campaign, and then says, okay, we need to make the first prototype, and they can't make it. This is a huge problem, right? This is the exact same case as the designer having to redo all the work, change the design, reduce capability. And so the greatest customers that we work with are the ones that went to somebody else who couldn't make it and now only have one way to make it. And then we're enabling something huge for them, right? Not only are we faster and cheaper, but we're also enabling the missile to have 10% higher thrust, 10% higher range. The reliability of the system to be higher. Maybe the cost is lower because they can do one part instead of 5 in some cases. And so those are really the best cases for us. That isn't everything. But when we can do that, it's a huge benefit for everyone.
Aeden, are you seeing, you mentioned their scalability, right? And the actual ability, and Cameron, we were discussing earlier, Freedom's Forge, right? For those, I think we've talked about it before. Awesome book. In good complement, a good sister book is Arsenal of Democracy. The benefit we had during that period was that there was this 2 to 3 year, if not longer, really 10-year period before December 7th, 1941, where the United States, because of what it was seeing geopolitically, was actually already putting in motion the movement towards scaling, right? I mean, you saw Ford already start converting some of its plans towards B-24s. You saw the work on Liberty ships. Obviously, that was a different year, different era. But are we seeing, the question I have is, are we seeing on the end customer side the actual drive and demand beyond low rate initial production, beyond just prototyping, to actually drive the rest of the manufacturing enterprise upstream to facilitate that?
No. I mean, we gave it all up. It's not here. When you don't make consumer goods here because you've hollowed out the consumer base, you don't have that surge capacity anymore, right? Who's gonna build this stuff? The factories for those parts aren't here. Even if a Ford is assembled here, they're getting a Bosch component from a casting house that's off in Taiwan or off in China or off in Mexico. Again, a lot of this stuff, they're screwdriver factories. So when you shut off that spout, like in the case of, if a balloon does go up, I don't think, if a balloon goes up, the faucet's going to probably be shut off. And they're going to be in the supply chains that exist under the all-American factories that exist today. So, they're making a car in Detroit, Michigan. That car is not being made with parts that are from Detroit, Michigan. It's unfortunate, but it's just the place that we're in. And so we need to shift that back. But I don't blame him, because that part can't be made on good margins at a good price with the weaponized subsidies that have been leveraged against us. And
it really exists in the shadows because we still think that that these cars are made in America for the factories that haven't moved yet, right? Most folks would just look at that level, say, okay, what factories of car making is still in America, but the ones that are here, Tesla's an outlier for sure. Tesla makes, I think it's like 70% of their cars are made with American parts. But the hard parts are really, if you just go on a quick deep dive here, neodymium magnet production. Almost all neodymium is processed through China. There's some stage of the neodymium process, the furnace step and the magnetization step that is done almost exclusively in China. There's a few neodymium magnets that are, all through NATO and allied supply chains, and the prices are, more than 15x what you'll find in America. But when you talk about these factories and the surge capacity, you aren't able to say, hey, you're making alternators for a Ford. Now go start making, motor components for these new autonomous systems or even your old legacy systems. There is no supply chain shift.
Yeah.
It doesn't exist.
It's compounding. It's not only there. The other aspect, I can't just turn a Model T plant or a Ford car plant into a B24 production line. It's just
not if you want American parts and
the different, right? A little. I mean, we're doing things that are arguably a little bit more complex. But your underlying point is, even regardless of that, we don't have the capacity. We've hollowed out the capacity here to be able to do it all the way upstream.
It's also worth saying that modern defense systems, I think, look a lot. The difference between a modern defense system and a car, and a World War II defense system and a car. I think the World War II, B-24 Ford, maybe a little closer than the modern systems. Like modern defense system, much closer to consumer electronics, right? It's lots of complex, electronics, lots of complex sensors and cameras, navigation, right? This is like closer to an iPhone than a car. And we don't make any iPhones here, right? Maybe we make some cars here, but the consumer electronics supply chain has really been built overseas. And it's really come into what the latest defense systems are as well.
Yeah. So if you guys you were czar for a day and you had 2 to 3 things you could do to reshape, reformat the manufacturing base here, what would that sort of look like? And maybe some specific sub-questions there is, would it be centralized, decentralized? Would you have edge nodes where it's closest to the potential user or operational standpoint? Obviously, we're talking both civilian and military.
By capacity.
That's it. It doesn't matter, whatever incentive structure works.
By capacity, by as much capacity as possible, and have contractual obligations on that capacity to go make the things that might be needed in the case of, a surge scenario. But there needs to be, look, at the end of the day, someone's got to make the parts. And the way that parts get made is you have machines and people that know how to use the machines. And one day they're cranking out one thing and the other day they're cranking out the other thing. And that doesn't exist because of the economics right now. So we have to at least match the subsidies of our adversaries to ensure that we have that when it comes time. But we have to start doing this now. The lead times on these factories are not a year. They're not even 2 years. I mean, in some cases, our foundry is looking at procuring equipment, which takes over 2 years from order to making the first parts. So this is a decision that you have to make even before you want the ability to use it or not. So you have to get on it quick. But I think the most certain path to maintaining the capability that is required, or building the capability that is required, is to buy capacity. I think the DoD can do this through a series of pre-existing mechanisms or through some new mechanisms. DPA Title III is a really great one with good history here, but it needs to be hyper-specific capabilities. So we're choosing a process, we're choosing a partner, we're choosing an application that's proven, to make sure that the execution side of this really works, right? Like this is one of the great things about a factory is you can't really put makeup on a part. Like the part passes qualification and you made it in X amount of time with Y amount of throughput or not, right? You can buy a factory that makes 12,000 doohickeys of X type for a Y platform. In the case of that platform needs to be scaled to 12,000 units a month. And you don't have to make that right now. You can use that capacity to build something else of a similar set of requirements. And that will feed back into the American private economy. But you need to have the option to be able to flip that switch. And today you don't have that option because you don't have that capacity.
So I know you all hosted Indo-PACOM Commander Admiral Paparo at the factory a couple months ago. I'm curious, how is DoD thinking about a capability like Rangeview in a future conflict in the Indo-Pacific in particular? And how will a conflict like that need different kinds of manufacturing capabilities than, say, what's happening in Ukraine or in the Middle East or elsewhere?
The Navy can't get parts right now. I mean, a sub will come back, a ship will come back, and there will be no way to get a part back on that system except cannibalizing another system. There's some crazy statistics out there for just how bad it's gotten, but the easiest way to look at it is for these new programs. They have a lot of funding behind them. We're throwing a lot of money at trying to build submarines. And if you look at the difference between the shipbuilding capability that America has versus our adversaries, it's astonishing. And if that's new stuff, if that's where everyone's focusing, imagine just how bad the sustainment and the maintenance component is. And so that's one of the biggest things that Paparo is interested in when he came by our Foundry and saw our technology. I think the flexibility of Rangeview, of offering a capability that can one day be making critical components for the private sector to shift when a submarine comes in and they need a ball valve, to be able to make that part on the spot is a massive capability that no other casting technology currently offers the Navy.
Yep. And there's a litany of congressional reports, and obviously the last reconciliation bill reflected a lot of the need to sort of recatalyze that. Specifically, Cameron, to what you just talked about, if a commander like the Indo-Pacific commander or just the DoD in general wants this flexibility, does it matter where it's produced? And what I'm getting at is, do we need some sort of edge manufacturing capacity? Does it matter where it's put? And does it actually make sense if we want to try and build that out?
Exactly. You're not going to print drones in the battlefield. It's just, it's actually more wasteful to send raw manufacturing goods to those printers. Manufacturing doesn't have an above 100% yield. It has less than that. So there's waste generated, right? So it is more space efficient and more material efficient to actually send pre-processed goods to the end use point than to ship the manufacturing plus the raw goods to that use point. And I've heard a few arguments. But what if the need changes? What if one day we need a drone that can fly 500 meters, and the other day we need a drone that can fly 1,000 meters? The work that goes into a drone design to achieve those two components is not work that can be done on the battlefield. It's work that's done pre-processed. They might load up some instruction file to the system. And the truth is that instruction file, whether it's the printer's job or the whole factory's job, can be programmed somewhere else. And you can, send 500 drones of one type and 200 drones of another. And the difference in that flexibility is far more beneficial than if you instead had an edge deployed system that touted to bring that flexibility to the battlefield. I don't think we've really seen it in look at Ukraine. Ukraine is not printing drones in the battlefield. Ukraine is shipping containers filled with thousands of these systems.
They're at least relatively close by from where those production facilities might be. There's a trade-off that has to be done, right, between the logistics and everything.
I mean, I think there's a pretty good razor as to when some sort of edge manufacturing makes sense. And actually, there's great precedent for this, right? We've had machine shops on aircraft carriers since they were new, right? Since World War II. The case that matters is if you have a very, very big, expensive system, which can be taken down by one or two spare parts. These cases are like the rare case when you want a little bit of edge manufacturing, because it will not be cheaper. It will be much more expensive. It will be much more painful to operate. The logistics of getting materials, maintenance to the actual edge manufacturing are going to be 10 times worse than they'd ever be on the mainland, but it's occasionally worth it if there's a really, really big system that needs to be kept up. And so there's some narrow cases. Most of the time, though, you really want a nice, safe, big factory that doesn't have to worry about operational security, doesn't have to worry about being bombed, doesn't have to worry about, the humidity changing because they're in a tropical, island and there's a rainstorm that happened, right? That's what you don't want in general. You want a big workforce. You want to be able to replace people quickly. If someone gets sick, right? The really obvious things. That's how you get to efficiency, and that'll be the bulk of all manufacturing forever. There are special cases, though, when for really big, expensive systems, you need to keep them up. You need to turn them around quickly. And there, edge manufacturing is a great solution.
What do you think is most misunderstood about manufacturing and reshoring from outsiders?
I think there's one thing to say, which is that people picture manufacturing as, just another thing. Like it's just another industry. And I think when you actually start to get into, what is manufacturing? Manufacturing is building the physical world, right? That is what manufacturing is. And the breadth of different kinds of processes, different kinds of things that are done, and the dependency between those, and how much, having a mine in a particular place can affect the price of valves. It is like mind-boggling to a lot of people. And I think, people forget, it's not just one process. It's not just like fixing magnesium supply in America does not fix the magnesium casting supply, nor does it fix the helicopter gearbox supply problem, nor does it have anything to do with the helicopter gearbox inspection problem, which are all distinct, huge problems with thousands of people that work on them in the US. And I think it's often forgotten just the scale of these things because, people don't see factories all the time. They don't walk down the street. They don't have friends that work in factories, right? We don't have this, especially if you go to the coastal cities, right? This is nowhere to be seen. And so I think people just lose some of the scale effect of, what are all the things that are going on and how do they depend on each other? And like how complicated it is to change something in manufacturing, right? If you want to change where something is manufactured, there's a lot of different pieces to it. I think that's a pretty big one.
For some context there, helicopter gearboxes are oftentimes magnesium. They're a very big supply chain problem. So you're just going to connect that lot. They're all magnesium problems, but there's probably $1 billion business in multiple of those magnesium problems. So you're shout out Magrathea, good company.
What advice do you guys have for other founders looking to build either in this manufacturing or national security, defense, industrial base space?
Never build a cost model. Just do it on vibes.
Don't start your own company.
Yeah, it's a hard one always, right?
Build a cost model day one. Update it every time anything changes.
We've already created so many competitors. There are literally two studies, but literally there have been 2 founders that just 100% because we've existed, right? So, I mean, even if we say build a cost model, don't go build robots, say one, we've probably spent hundreds of thousands of dollars on that lesson, right? That's actually a pretty big lesson. Purchase Rangeview's system. No, and
use Rangeview to make your parts.
Yeah, and
don't build software. Build an actual company that makes parts. Build a factory. Those are up there.
Yeah. So for other startups, focus on how many parts you make a day. That's the metric of success that matters. We need parts, not tools for someone else to maybe go make parts. Make parts yourself. Go make a factory. Don't build software for a factory that may want to use yours. Factories don't want to use software. This is why we're in this space. Go build a factory and make lots of parts and make your internal success metric proportional to how many good parts you're shipping a day.
Who are you looking for to come join Rangeview, Cameron?
Oh, anybody who's tired of working on stuff that might not matter as much, not to say I think it's important that the work that you do matters. I think you gotta wake up and look around and say, beyond the money, what are you doing? Your career is going to take up the vast majority of your life, right? What are you doing with that career? What are you doing with the world?
And if you're an engineer, really principled, strong mechanical engineer, software engineer, if you love to learn about castings, please, I didn't want to plug it here, but our website has a careers link. You click on that. We're expanding our team like crazy. If you want to build custom vacuum induction melters, if you want to come work on the next generation of 3D printers, if you're excellent at what you do, I would love to speak with you, and we can build this cyber foundry together.
Awesome, Cameron. Where's the company going to be in a couple years? What's the vision?
Yeah, we need another Westinghouse, don't we? We need someone that's making the world stuff, and I think that's going to end up with folks that understand the new paradigm. I think that's folks that understand modern technology as it relates to manufacturing, and folks that understand automation. I think we've got a pretty amazing team here, and I think everyone here is doing it for the right reason. So I'd hope to be making a lot of parts.
Awesome. Well, Cameron, Aeden, this has been awesome. Thanks so much for taking time. Excited for what you have already built, what you're unlocking, both in what can be built going forward, what is new and possible, and what can be scaled going forward. And excited to be part of the journey with you. Hey, everyone. Thanks for listening to the Mission Matters podcast from Shield Capital. Tune in again next month for another conversation with founders building for a mission that matters. And if you yourself are looking to build in the national security space, please reach out to us.